Hi, welcome back. In this set of lectures we're talking about Markov models, and in the previous lecture I introduced what they were, how they're these finite set of states and there's transition probabilities between those states. What I want to do in this lecture is just show you how a simple Markov process works. So we're going to take a very, very simple Markov process and work through it, see exactly how the dynamics unfold. And in doing so, we're going to learn how to use matrices, specifically how to multiply on matrices. Okay, so let's take our simple example, and let's do the case of the alert and bored students. So I'm teaching a class, like many people do. This is an online class. And there's some percentage of people that are alert, and there's some percentage of people that are bored. Now what's going to happen at any given moment in time, someone who's alert could switch and become bored, and someone who's bored could switch and become alert. And what we want to do is we want to understand the dynamics of that process. We want a model that helps us understand these dynamic processes where there's these states, alert and bored, and people move between them. So we got to make some assumptions. We've got the two states, alert and bored, and now we need to understand the transition probabilities. So we need to assume something about transition probabilities. So let's assume the following's true, that 20% of the alert students become bored, but that 25% of the bored students suddenly say, hey, that sounds interesting, these Markov processes sound really cool, and they become alert. So that's what we want to model. So we can think of that as we've got the set of alert students, 20% of them are going to become bored, and of the bored students, 25% are going to become alert. So we can draw this picture, but this doesn't help us much. We want to sort of figure out what's going to happen, and this is where the matrices will be useful. Now before we do the matrices, let's just try and do it by hand. So let's start with the scenario. We've got 100 alert students. So if I have 100 alert, let's say A is 100, and bored is 0, and I know that 20% of the alert become bored, and the rest are going to stay alert. So that means that what's going to happen is I'm going to then have 80 alert, and I'm going to have 20 bored. Well, now I've got to think, okay, what happens next? What happens next? I know that of the 80 alert, I know that 20%, which is 16, are going to become bored, and the rest, 64, will be alert. Now the 20 that are bored, I know that 25% of that is 5, so I'm going to put 5 of those become alert, and I'm going to know that 75% of it, which is 15, stay bored. So what I'm going to get is 69 alert and 31 bored. And I can say, okay, now I've got alert 69 and bored I've got 31, and now I've got to do this again. I've got to think, okay, well 20% of these, which is going to be 13.8, become bored, and so on. And this you think, okay, this gets really complicated, and I've got numbers all over the place. Maybe there's a better way. Maybe there's, instead of writing all these numbers with these arrows, there must be a simpler way to keep track of all this. Well, there is, and the idea is something called a Markov transition matrix. And here's the idea. We basically write down the probabilities of moving from state to state. So these columns tell us what's true at time t, and the rows tell us what's true at time t plus 1. So if you're alert at times t, there's an 80% chance you stay alert, and a 20% chance you become bored. If you're bored at time t, there's a 25% chance you become alert, and a 75% chance that you stay bored. So this gives us just a matrix representation, a simple representation of all these transition probabilities. Now the reason this is useful is then we can just multiply these matrices to see how the transitions unfold. So here's an example. Suppose I start with 100% or 1. This is just a probability. So with probability 1, someone's alert, and I want to figure out how many alert people are next time. Well, this number, this 0.8, tells me the percentage of alert people that stay alert. So I'm going to get, so I take 0.8 and I multiply it by the 1, and that gives me 0.8. Now I want to ask how many bored people become alert. Well, 25% do, and how many bored people were there? Were 0, so I'm going to get 0.25 times 0, so I end up with 0.8. So the way I multiply matrices is I basically take this row here and I multiply it by this column. Now let's make this more formal. So what I do to multiply these things out is I've got, here's where people go at times t plus 1. This is how many are going to be alert at time t plus 1. 80% of the alert people and 25% of the bored people. Here is the percentage of alert people and the percentage of the bored people. So I want to know how many are going to be alert next time. It's 80% of the 1 and 25% of the 0, and that's going to end up being 0.8. Now I want to ask how many are going to be bored. Well, 20% of the alert people and 75% of the bored people. So I take this row and also multiply by the column. So I take 0.2 times 1 and 0.75 times 0, and I get 0.2. So what you get is, when I multiply this matrix, the transition matrix here, by this initial vector 1, 0, I get 80, 20, just like I did before. Remember, the way I did that is I take this row, multiply it by the column, and then I take this row and multiply it by the column. Well, watch, now I can do it again. Now I'm at 80, 20, and I want to ask how many am I going to get next period? Well, I take this row, 80, 25, and multiply it and say 80% of the people are alert, 80% of them stay alert, so that's right there. 20% are bored, 25% become alert, so that's right there. And when I add those up, I'm going to get 69. And here I'll get 31. Well, let's see what happens in the next period. Again, just take this row times this column. So of the 69% that are alert, 80% of them stay alert. And of the 31% that are bored, 25% of them become alert. And I get that 63% are alert. And then I can do it again and take 0.8 times the 63 and 0.25 times the 0.37 and get the new percentage that's alert, which is going to be 60%. And I can keep going and going and going. And if I do it one more time, I end up with 58%. So what does that tell us? That tells us that if we started with all alert students, after 6 periods, I'm going to end up with 58% of students being alert. Now we want to know, where does this process stop? Is it going to go end up with nobody being alert? Well, let's think that through. Let's suppose we started out with nobody being alert, and we can ask what happened. So if I started with all bored students, what's going to happen? Well, now all I do is put a 0 for the alert and a 1 for the bored, and ask what happens next. Well, 80% of these alert students will stay alert, but that's 0, so it's 0.8 times 0. And 25% of the bored students will become alert. So that means I'm going to get 0.25, and that means, since this sums to 1, I'm going to get 0.75 over here. Next period, I've got 25% of the students are alert and 75% are bored. Well, now I can just put that here as my population at time 2, and I can think, okay, of these 25% that are bored, or alert, 80% will stay alert. Of the 75% that are bored, 25% become alert, and if I multiply all that out, I get that 45% are alert, 55% are bored. If I do it again, I'll end up with an even number of alert and bored, and if I do it one more time, I'll get that 53% are alert and 47% are bored. So it sort of looks like this is going to an equilibrium. When I started out with everybody alert, I got down to 58% alert. And when I started out with everybody being bored, I ended up with 52.5% being alert. So it looks like it's converging somewhere between 53 and 58%. Well, how do I find what that equilibrium is? This is where the matrices become really powerful. So let's think of it this way. There's some percentage of people that are alert. That's P. And there's some percentage of people that are bored. That's 1 minus P. What I'd like is, after this process takes place, for the same percentage to be alert. So how many are going to be alert? Well, that's going to be 0.8 P plus 0.25 times 1 minus P. So what would it mean for there to be an equilibrium? Equilibrium would mean that after I multiply this out, I have the same percentage of people being alert. So the equilibrium, I put a little star here, is going to be the P star such that 0.8 P star plus 0.25 times 1 minus P star just gives me P star back, that I end up with the same percentage of people alert that I started. This just becomes algebra. I can now write this out. I've got an equation where this is my Markov transition matrix, and I want some probabilities P of people being alert such that after the transition I've got P back, right? So that's just going to be 0.8 P plus 0.25 times 1 minus P should equal P. I want to find the P that solves this. Well, let's multiply through by 20 just to make this simpler. So I'm going to get 16P plus 5 times 1 minus P equals 20P. So that's going to give me 16P plus 5 minus 5P equals 20P. And so if I bring all the P's over to the one side, I'm going to get 5 equals 9P, so P equals 5/9. So what that says, if I start with 5/9 of the people being alert, I'm going to end up with 5/9 of the people being alert. So let's think about how that works precisely. So 5/9 of people are alert. What do we know? We know that 20% of them are going to become bored. So that means 20% means that each period 1/9 of the population will become moved from alert to bored. I also know that 25% of the bored people will become alert. What's 25% of 4/9? That's also 1/9. Right? So what I get is that so each period 1/9 of the people are moving from alert to bored, and 1/9 of the people are moving from bored to alert, which means that exactly 5/9 stay alert and exactly 4/9 stay bored. Now notice what this equilibrium is like. It's a statistical equilibrium. So we can think of an equilibrium point where nothing changes. Here the thing that's not changing is the probability. So the population is still churning. People are moving from alert to bored. But if I think in terms of probabilities, that probability is staying fixed. That probability is staying fixed at 5/9. People are moving around, but the probability is staying fixed. That's why this is sometimes called a statistical equilibrium, because the statistic, P, the probability of someone being alert, is the thing that doesn't change. Okay, it's pretty involved, right? What we did is we wrote down the Markov transition matrix, and we showed how using that matrix we could solve for an equilibrium. And we saw, at least in the simple example of alert and bored students, that the process went to an equilibrium, and it was fairly straightforward to solve for it. What we want to do next is we want to do a slightly more sophisticated model that involves multiple states instead of just two, involves 3 states, and we'll see how that process also converges to an equilibrium. Thanks.